Welcome to Maths with EJD. In this video, we move on to the separation of variables for the Laplace equation. So just like I have done the same for heat equation and wave equation, we are using separation of variables for Laplace equation. These are the top three equations we've been talking about since I started talking about partial differential equations. So it's an overview. The Laplace equation is a second order partial differential equation given by nabla squared u equals 0. So in Cartesian coordinates, for a function u of x of y, u of x comma y comma z, this equation becomes partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared equals 0. Okay. Now, to solve this using separation of variables, we assume the solution can be written as a product of functions, each depending on a single coordinate. Specifically, we assume that u of x comma y comma z equals x of x, y of y, and z of z. Okay, so here x of x, y of y, and z of z are functions of their respective variables only, So here, the first step one, will be to substitute. So substituting into the Laplace equation. Substituting into the Laplace equation. So we have partial squared u partial x squared equals x prime prime of x, y of y, z of z. Okay. And on the other hand, we have partial squared u partial y squared will be x of x, y prime prime of y, z of z. And lastly, we have partial squared u partial z squared, and that will be x of x, y of y, and z prime prime of z. Okay, easily. That's partial squared z, partial z squared. That's big Z up, small z down. Okay, now substituting this into the Laplace equation gives x prime prime of x, x prime prime of x, y, x prime prime of x, y of y, z of z, plus x of x, y prime prime of y, z of z, plus x of x, y of y, z prime prime of z is equal to 0. Okay, so we go for step 2. So in step 2, we divide. Dividing by x of x, y of y, and z of z. So in that case, we can separate variables. So to separate the variables, we can divide through by x of x, y of y, z of z, the original function, the original separated function. So it's more like divide each one by that, x of x, y of y, y of y, z of z. So this way, y of y will cancel, z of z will cancel. So you have x prime prime all over x prime prime of x all over x of x. If you come here, it's the same. So this will cancel, and you have y prime prime over y. Here, this will cancel. So you have z prime prime all over z. So with that, we can move on to what I'm going to write out next. So that we would have effectively separated the variables, and that's where the idea of separation of variables come. So by dividing through by that, as you can see, we have x prime prime of x all over x of x plus y prime prime of y all over y of y plus z prime prime of z all over z of z. And all of that is equal to 0. So that is done. We can move to step 3 now. So in step 3, we have the separation of terms. Separation of terms. So this is where we introduce coefficients of separation like we saw previously. So here, each term in the equation, depends on a single variable. So for this equation to hold for all values of x, y, and z, each term must be equal to a constant, and that is what we call the constant of separation. So here, thus, we set x prime prime, that's looking like alpha, let's do it better, x prime prime of x all over x prime prime of x all over x of x is equal to minus lambda 1, okay? And then we have y prime prime of y all over y of y equals minus lambda 2. And then we have z prime prime of z all over z of z equals minus lambda 3. So, okay, first one we have minus lambda 1, second one we have minus lambda 2. For this one, let's have it as lambda 1 plus lambda 2. So first one is minus lambda 1, second one is minus lambda 2. For this, we have it as, I think it will help us simplify in the future. So we have lambda 1 plus lambda 2, okay, instead of just minus lambda 3. So now you see that this separation, now this results in 3 ordinary differential equations. So the first is x prime prime of x plus lambda 1 x of x equals 0. Then we have y prime prime of y plus lambda 2 y of y equals 0. And then we have z prime prime of z minus lambda 1 plus lambda 2 z of z equals 0. So we have these three equations now. So the next step, which is step 4. So in step 4, we are solving the ODEs, solving the ordinary differential equations. Interestingly, they are all second order stuff, whose solutions we can easily know based on our experience solving differential equations. So each of these is a standard second order linear ordinary differential equation whose solutions are determined by the values of the constants lambda 1 and lambda 2. Okay, so for x of x, the general solution is x of x equals a cos square root of lambda 1 x plus b sine square root of lambda 1 x. So that's for x of x. Now, for y of y, the general solution is y of y equals c cos square root of lambda 2y plus d sine square root of lambda 2y. Okay, and then for z of z, the general solution is z of z now, because that is negative, so we can have e raised power e square root of lambda 1 plus lambda 2 plus f e raised power minus square root of lambda 1 plus lambda 2. So that's for z of z. Then that takes us to the boundary conditions in step 5 now. We'll talk about the boundary conditions. So the specific form of the solution the specific form of the solution depends on the boundary conditions of the problem, on the boundary conditions of the problem. For example, if the domain is a rectangular region, the boundary conditions will determine the values of lambda 1 and lambda 2, which could be discrete eigenvalues based on the geometry. Okay, so okay, let's switch now. We can have this, while this can be okay, this. Okay, so example, let's solve Laplace equation in a one-dimensional rod. Okay, so Laplace equation in a 1D rod. Okay, so consider the Laplace equation for a function u of x on the interval 0 is less than or equal to x is less than or equal to L with boundary conditions u of 0 equals 0 and u of L equals 0. The Laplace equation is partial squared u partial x squared equals 0 because we are talking about one dimension. So if you now assume a solution of the form u of x equals x of x. It's one dimensional, by the way, so no worries. So where x of x satisfies that x prime prime of x is equal to 0. Okay, so the general solution is x of x equals c1. I mean, it simply means that the whole thing is constant, right? So x of x is c1 of x. Normally it's constant c2, but then if we need to take another constant because we need two solutions, so we now have another constant multiplied by x. So we have c1 of x plus c2 like that. That is the general solution in that case for a one-dimensional rod. So if we now applying the boundary conditions, okay, so we have u of 0 equals 0, which implies that C2 is 0 because u of 0 equals 0. So when x is 0, we just have C2 to be 0 from here. So because u of 0 equals 0, that means this is 0 when x is also 0. So we have only C2 left, which is this 0. That's why we have that. Or I mean, let me be explicit about that, right? I have not much anything to lose by doing that. Okay, so we have this. So that means that u of x plus c1, I mean u of x, which is equal to c1 of x plus c2, will imply that 0 is equal to c1 times 0 plus c2. So this goes, so c2 is simply 0. That's what this implies. Then we have the next condition that u of L is equal to 0. So that means that, you know, when x, so this simply means that when small x is equal to L, u is 0. Just like here, or what this meant was when x is equal to 0, the u itself is 0. That's how we have that. So in this case, we just have for that x of x. Okay. Yes, I mean that works. All right. So here now we have x of x equals c1x plus c2. So that means this place is 0 when x is L. So we have C1L plus C2. So C1L plus C2, And since we already know C2 is equal to 0, right? From here, C2 is already equal to 0. So since C2 equals 0, so we have 0 equals C1L plus 0. So basically, C1L is 0, and then C1 is simply 0 because this implies that C1 is equal to 0 all over L. So C1 and C2 are both 0. In that case, we can say thus the solution to this specific problem is u of x equals 0. Okay, so the it's stationary, right? That means meaning there is no non-trivial solution. There's no non-trivial solution in this case. So that means all the solutions are trivial. Okay. Now, if we go two-dimensional, right, things can become more complicated. So in more complex geometries, so here we are talking about a one-dimensional rod. If you go two-dimensional, where we have X and Y, we may not expect to have this kind of results. So in more complex geometries or higher dimensions, the boundary conditions would lead to eigenvalues lambda 1, lambda 2, and so on and so forth that generates a series solution. Okay. All right, so that's the end of separation of variables for Laplace equation. Okay. But of course, in the future, I think we're going to be seeing Laplace equation with different kinds of boundary conditions. But for now, let it suffice this way. So let's take some practice questions. Just try your hands. Generally, when we looked at the idea of Laplace equation, right, it talks about it describes stationarity most of the times. So consider the Laplace equation in a rectangular region. So here we have a rectangular region, so where you have 0 less than or equal to x less than or equal to L, and you have 0 less than or equal to y less than or equal to h. That's something like length times height because it's rectangular. So, and the Laplace equation itself is partial squared u, partial x squared plus partial squared u, partial y squared equals 0 with boundary conditions, u 0 comma y is 0, ul comma y is 0, ux comma 0 is 0, ux comma h is also 0. Okay, so the question is the separation of variables method to find the solution to this problem. That's question 1. Let me look for another one. Okay, the other thing we want to talk about is polar, maybe something in polar form. Okay. Yeah, let me just drop this simple. Maybe not quite simple. I mean, when you change coordinates, things can become really complicated, like we saw yesterday for canonical form. So let's look at the second example on Laplace equation in a disk. So consider the Laplace equation in polar coordinates. In polar coordinates for a disk of radius r, which is 1 over r partial r into r partial u partial r plus 1 over r squared partial squared u partial theta squared equals 0. So now we have r and theta in polar coordinate, right? Instead of x and y, we have r and theta with boundary conditions. U r theta equals 0 for all theta. So the question is to solve this problem using separation of variables and determine the possible eigenvalues. The possible eigenvalues. Okay, so you want to solve this, and let me see your answers in the comment section, either on Facebook or on YouTube. You also want to let me know how helpful these videos are for you. And of course, if you have a problem you like me to solve or a topic you like me to teach on, feel free to indicate also. Then if you have subscribed, thank you. If you have not, please go ahead and subscribe. And everyone, don't forget to hit the notification bell so you can always get alerted each time a new video is released. Lastly, be sure to like and share so that more people can have access to this great content we have here. Till I come your way again, keep doing math right. In the next video, I think I'll be talking about Fourier series and partial differential equations. You will definitely want to see how that goes. Till I come your way again, keep doing math right. Bye.